reference. Share ko na yung yung lecture. Kita na ba yung screen, class? Hello? Hello? Okay na screen?
Okay na po, sir.
Okay. Sagot kayo. Hindi ko kasi alam kung nandyan pa kayo or nandito kasi sa screen. So we're gonna start yung lecture
Okay na po.
na we decided na mag-online na lang. Di ba? So the laboratory to, the ME313L, no? Kasi lab naman, i-discuss na lang natin kasi nag-request kayo na na 'di ba mahirap pa magbiyahe ganyan no. So we're gonna start yung ating topic about fracture toughness, no. So ano bang ibig sabihin nito? The critical stress intensity factor of a sharp crack where propagation of the crack suddenly becomes rapid and unlimited. Yan. So yung fracture na binabanggit dito ay may kaugnayan dun sa paraan ng pagkasira niya and then how it propagates, no. Yung mga metallurgists alam niya, no, ina-analyze nila yung structure, makikita nila kung paano nag-propagate yung crack sa nag-start, no. Another definition is the resistance of brittle materials to the propagation of flaws under an applied stress, and it assumes that the longer the flaw, the lower is the stress needed to cause fracture. Yun, no? So yung propagation ng binabanggit dito, yun ang fracture toughness. Meron tayong tinatawag na linear elastic. Tingnan nyo rito, no? Mode 1. Mode 2, parang shape. Ito naman is parang like a lateral, no, sa horizontal. Yan. Meron tayo dito. We can use the graph. No, we can plot the graph. Yung fracture toughness which is represented by the variable K sub C and the thickness, no? So anong masabi natin dito? How do we interpret yung graph? So how do we interpret yung graph? So makikita mo dito, naka-inverse, no? Naka-inverse relation siya. It's the graph is going down. Ibig sabihin pag mataas yung toughness, may piece, di ba? If you take a look at this, yung ng pen. Di ba dito, ayan o. Ay, ba yan? Sorry. Naka-mouse lang kasi ako, no? Wala, hindi ko pa na-install yung digital. Ibig sabihin pag mataas yung fracture toughness natin, manipis yung thickness, no? Ngayon, pag kumakapal na ganyan, bumababa naman yung toughness natin, no? Ayan, no? Makapal na. So, makapal na thickness dito, mababa na yung fracture toughness natin. No? And then we go to fatigue. Ano mong naintindihan dun sa salitang fatigue? Sa ordinaryong salita, sa ginagamit yung fatigue? Saan ginagamit yung fatigue? Ano yung Tagalog ng fatigue? Fatigue? Anong fatigue, Hana? Hana, nandiyan ka ba, Hana?
Yes po, sir.
Ano sa Tagalog yung fatigue? Saan natin ginagamit yun?
Ano po, parang pagod po yun, sir. Yung sobrang pagod.
Pagod, 'di ba? Pag bakit ka napagod kasi paulit-ulit nakakapagod, paulit-ulit. So, ibig sabihin, may repeated ka na mga naramdaman or stress, 'di ba? So, ganun din may relate natin sa material kasi paulit-ulit yung mga stress tsaka load. So, ang tawag ay cyclic na cycle na paulit-ulit, no? So, fatigue. For example, yung piston, 'di ba yung piston may piston rod. Ito, halimbawa yan ang piston, di ba? Ito yung cylinder. Pasensya na sa drawing, naliliko-liko kasi mouse lang to. Yan. So, ito yung piston, di ba? Yung cyclic load yan kasi paulit-ulit, di ba? Cycle per second. Madami beses habang umaandar yung engine, no? So, we can define fatigue properties. A phenomenon leading to the fracture under repeated or fluctuating stress having a maximum values less than the tensile strength of the material. So repeated yung fluctuating stress niya, paulit-ulit, but it is less than the the maximum tensile strength. Fatigue fractures are progressive, beginning as minute cracks that grow under the action of the fluctuating stress. No? So titingnan nyo dito yung no, pag pinag-usapan yung mga fatigue, no, tinitingnan natin yung kung saan nagpo-propagate una, no, minute cracks, ibig sabihin maliit na crack tapos propagate, no? Magtutuloy-tuloy na yan. No? So meron akong definition dito. Nakikita nyo ba to? Di ba? Yan yung crank. Saan ginagamit? Di ba? Yung crank. Ginagamit yan sa mga moving parts. Di ba? Yung paraot parito, to and fro crank. No? So yung crank na yan, nagawa sa aluminum, pag inanalyze ng mga metallurgists, the dark area of striations, ito. Pag nakita nyo to, although hindi naman tayo magpapakalalim dito kasi ano to ng ano, di ba, ng mga metallurgists, porte. Pero it will give us a better understanding, di ba? Ayan. Yung itim na yan, di ba? Yun yung yun yung striations, no? Slow crack growth. So dito nag-umpisa yung crack na grow. Then the bright granular area, ano yan? Ito. Bright sudden fracture, no? So dito dahan-dahan siya. Ito, mabilis na. Sudden na. Yan, di ba? So yung mga metallurgists, mga nag-aaral ng metals, no, ina-analyze nila sa structure yan. Mga structure na ganyan. Na using yung mga SE, yung mga iba't ibang mga klase ng mga makina. or machine, no, na madaling makapag-analyze ng structure. So, ano ba yung fatigue? Ito, yun lang ang maintindihan natin dun, okay na lang. So, fatigue is the initiation and propagation of cracks. Kung papaano nag-i-start and then papaano nagtutuloy-tuloy, nagpo-propagate yung crack, no? Fatigue yun. In a material due to cyclic loading, di ba? Pag repeated, di ba? Sabi natin, pag repeated, paulit-ulit, repeated stress, pasensya na kasi mouse lang ang gamit ko, ha? Repeated stress, no? Cyclic. So yung mga keyword natin ay cyclic loading, tapos yung initiation, kung paano nag-start at nag-propagate yung crack, no? So once a fatigue crack has initiated, it grows a small amount with each loading cycle. So pag paulit-ulit na nag-start na yung crack na yun, tapos tuloy-tuloy na, ang mapuproduce ay yung ito, how do you pronounce this? Striations. On some parts of the fracture surface, ito nga, itong itim na to, yun yung striations, nagsimula siya ng mabagal, no? The crack will continue to grow until it reaches a critical size, which occurs when the stress intensity factor of the crack exceeds the fracture toughness. Ito yung pinag-uusapan natin kanina, may fracture. Yung fracture toughness, ito. Yan. Di ba? Fracture toughness. Producing rapid propagation and typically complete fracture of the structure. So ito na yung rapid, no? Sudden or rapid, yan. Rapid. Ito naman ay slow. Di ba? Stration yan, stration yan. Para lang ma-imagine natin. Okay? So yun yun. So ano naman yung fatigue life? It is the number of loading cycle. No? Kung ilang beses yung cycle of a specified character that specimen sustains before the failure. So kung ilan yung cycle bago siya bumigay, bago siya mawasak, no? Bago siya masira. Number of cycle. Yun ang life. No? Kadalasan ginagamit yan sa mga reliability study. So ano yung mga stages nun? Slow crack initiation, di ba? Sabi natin, slow crack initiation, sa nag-umpisa yun, ito. Dito sa maitim na to, dito nang galing yung slow muna. Dahan-dahan naman yan. Tapos, stable crack root and rapid crack. So, may mga stages. Ano? So, ito yung mga topic na under ng fatigue, no? I think sa mga dating sa mga dating klase ni Ma'am Abel, no? Pero ito yung mga topic, no? Fracture toughness, fatigue, NDT, non-destructive testing, ginagamit yan sa pagtetest ng ng metal na hindi gumagamit ng pagkasira ng bakal or ng mechanical, no? Alam naman natin yan. Ano yung mga NDT? Ito yun. Ultrasonic, na? Yung UT. Yan, di ba? Tapos radiography o X-ray, radiography, yun ang ginagamit sa pag ng measure ng mga fatigue din. Then yung eddy current yan. Tapos yung empty magnetic particle. Then itong dye penetrant. Okay? So tingnan natin kung ano bang gusto niyo makita dito, no? Ultrasonic radiography. Dali. Lista ko lang, tapos titingnan natin doon sa YouTube. Ultrasonic Class, nadidinig ba yung ano? Nadidinig yung sound? Hello? Class? Nadidinig ba? Nadidinig ba yung ano? Nadidinig ba yung video, Hana?
Wala po, sir. May video po pero walang sound po.
Walang sound. Sige, sige. I-ano ko, i-tab ko na lang ha. Baka kasi ano. Kasi ang purpose lang natin nito, kaya na pumayag ako sa online is para makita nyo kung ano yung mga testing, no, sa mga non-NDT like ultrasonic, radiography, magnetic particle, tsaka dye penetrant. No? Kasi otherwise mahirap explain yun kung nasa face-to-face tayo. So, i-ano ko muna, no? I-stop ko muna, i-ano ko yung tab. Gamitan natin ng ano, yung tab mismo.
Non-destructive testing. Ultrasonic examination.
Ana, okay na? Ana?
The basic principle of ultrasonic testing of materials is the propagation and reflection of sound waves. As an example, a cylindrical workpiece is shown in the animation. The longitudinal section through the cylinder shows the position of the atoms, extremely magnified and simplified as a single crystal. To begin with, a rigid unyielding stop is attached to the right front end of the cylinder. At the left front end, a disc is installed. It will be used to transmit and receive sound waves. Pushing and pulling briefly at the disc causes a longitudinal sound wave to propagate through the cylinder. When the sound wave reaches the rigid stop at the right side, it is reflected and runs back towards the disc, which now serves as a receiver. A free end is also able to reflect a wave. In this case, however, the tensile side runs ahead in the reflected wave and finally deflects the receiver to the right. The reflected wave is even reflected again and actually travels for several times across the length of the cylinder. but this is not shown in the animation for the sake of simplicity. So, if a sound wave is generated at one end of a workpiece, it will travel through the material with its speed of sound. At the free end of the workpiece, the sound wave is reflected and it returns to the transmitter, which then acts as a receiver. For ultrasonic testing of a workpiece, not a large transmitter is used in most cases, but a rather compact one, which generates a short ultrasonic pulse. At a place free from defects, the ultrasonic pulse travels to the right front end, also termed back wall. The pulse is reflected and recorded again as an echo. When the transmitter is moved a little downwards, the cavity reflects a part of the wave. That part arrives earlier at the transmitter than the rest of the sound wave. Even further downwards, the cavity reflects the complete ultrasonic pulse. For material testing, either the echo of a defect can be utilized, this is the pulse echo mode, or the phenomenon that hardly any sound waves pass through the imperfection. This is called the through transmission mode. In pulse echo mode, a transducer installed in a probe performs both the sending and the receiving of the ultrasonic pulse. On a computer monitor, the intensity is being plotted upwards on the y-axis and the time towards the right on the x-axis. With the probe at a place free from defects, only two signals may be seen on the monitor: the transmission pulse and the echo resulting from the lower surface of the workpiece, termed back wall echo. Moving the probe towards the right leads to an additional echo created by the defect. Even further towards the right, only the defect echo is visible apart from the transmission pulse. In our laboratory, there's a green-painted steel cylinder to be found. It contains artificial defects which are invisible from the outside. To track down the defects, the material tester uses the pulse echo method. This is how a typical probe looks like. Under the bright wear plate, a piezoelectric disc is installed. It can transmit and receive ultrasonic pulses. A computer operates the probe via a plug-in card and power electronics. On the monitor, the intensity is plotted upwards and the time is plotted to the right. After placing the probe on top of the cylinder, initially no echo at all may be seen on the monitor. The reason for this is the too small contact area between the probe and the workpiece. Only with the use of a gel, the so-called couplant, the ultrasonic pulses can get into the workpiece and can also go back into the probe. Now the back wall echo turns up on the monitor. The material tester spreads out the gel evenly on the top surface. That way she is able to examine the entire cylinder.
So mapapansin nyo, no? Hindi to basta-basta, kumbaga there's a trained technician for this, or there's a trained engineer for this, no? Merong probe, tapos merong material. Hindi mo basta ginagamit yan ng ganun-ganun lang, no? Merong mga procedure, and one of the procedures is you have to use gel, no? Parang papahiran mo ng gel yung surface para maka-receive ng sound, no? Kasi ultrasonic to eh, para mag-reverberate or makapag-absorb siya ng sound, no? So without the gel, hindi siya mag-respond, no? So yun ang point lang natin dito. And then eto naman ay may software na, no, real time. Pag pinahid-pahid mo diyan, para siyang ultra, 'di ba, para pang ultrasound, 'di ba? Ultrasound yung mga buntis, no, nanay, or may buntis kang asawa or kapatid, 'di ba, ganyan. Or pag nagpapa-check up ka ng mga internal organs, no? So ganyan din, may probe tapos may gel na pinapahid, no?
Using the velocity of sound in the material, one can plot the calculated depth on the monitor to the right instead of time, a very useful feature. With the help of so-called trigger gates, which may be set on the echoes with a computer mouse, the depth of the defects can easily be read off at the lower left-hand corner of the monitor. The cylinder back wall lies in a depth of about 200 millimeters below the probe, so the cylinder has a height of 200 millimeters. And here we go. The material tester scans the upper front end of the cylinder with a probe and observes the monitor. A defect echo appears on the monitor. This defect is located in a depth of 130 millimeters below the surface. Another echo indicates a defect in a depth of 87 millimeters. The second, smaller echo at 174 millimeters is caused by double reflection on the same imperfection. And these are the defects. A drill hole and a saw cut. Filled up near the surface and painted, they are not visible from the outside. The drill hole in a depth of 130 millimeters. The saw cut 87 millimeters below the surface. Trams are popular means of transport in Karlsruhe in southern Germany. The tram cars are not only cleaned regularly, but also tested thoroughly in regular intervals by the transport company. Among many other maintenance points, the ultrasonic examination of the wheel axles plays an important role. A tram enters the maintenance hall for inspection. Some of the tram cars have already been lifted up. That way the bogies can easily be detached, pushed forward and examined carefully. This is one of the bogies jacked up to comfortable working height and prepared for ultrasonic inspection. Special attention is given to the wheel axle, among experts known as wheel set axle. It has been designed as a hollow axle. This saves weight and facilitates the ultrasonic examination. The material tester applies a suitable oil as a couplant into the bore of the axle. Now he takes a special probe designed exactly for this purpose, inserts it carefully into the bore with a mount, and evenly spreads out the couplant by turning and pushing. He has accurately marked the most important examination points at the mount. In an experienced manner, he positions the probe at the appropriate places within the wheel set axle and watches the monitor closely. The probe has specially been designed for this application. It transmits the ultrasonic pulses at an angle of 45 degrees. At a place without defects, no defect echo returns. But when the pulse encounters a crack which has grown in from the outside, double reflection occurs and a typical defect echo is recorded. It is important to note that also the shape of the wheel set axle may lead to an echo, for example at shoulders. These are so-called contour echoes. In this particular case, only contour echoes are recorded. No abnormality has been detected. The wheel set axle is perfect and can be used again to transport many passengers until the next examination becomes due.
May sound ba dyan, Hana? Yung sa pipe, may sound ba?
Alin po
May
yun,
sound ba
sir?
dyan?
Opo.
Sa pipe, sa pipe. Ano ba yung sa pipe? Nakikita ba?
Hindi po, sir.
Hindi?
Yung kanina
sige.
pa lang din po ito, yung sa ultrasonic po.
Sige, sige. Itatap ko ulit. Sandali
It can detect
Yan, okay na? Okay na?
Okay na po.
Sige, sige.
Hello
Tingnan natin
everyone.
yung sa
Good
pipe
morning,
application.
good afternoon, and good evening. It's me again. Today, we're gonna show you some professional things ultrasonic testing. As you know, non-destructive testing is a testing method for inspecting the surface and internal quality of the inspected part without damaging the workpiece or raw material. According to the research and analysis of NASA, it is believed that non-destructive testing methods can be divided into 6 categories and about 70 kinds. Ultrasonic testing is one of them. It can detect, locate, evaluate, and diagnose various defects in a workpiece quickly and accurately, including welds, cracks, inclusions, folds, pores, blisters, etc. Can be used both in the laboratory and on the engineering side. In this video, we're using the ultrasonic testing detect our welded pipe to ensure the quality of our products can perfectly fit the requirements of our client. Obviously, we passed the test like we always do. Appreciate for your time. Hope you guys enjoyed the video. Don't forget to give us a like and subscribe our channel. Let me know your think down on the comments. Thank you again for watching. I'll see you next time.
So tingnan naman natin yung radiography, no? Kasi ano yun, yung una is ultrasonic, yung radiographic, no, or yung X-ray. Tingnan natin. Maghanap muna tayo, ha? Kasi kailangan itab muna siya, eh. Nakikita na ba, Hana? May sound ba?
Yes po.
Sige. Radiography na tayo, ha?
This short video will show the method of radiographic testing inspection by using gamma ray radiation source. There are a lot of techniques of RT inspection. In this short video we'll show some of these techniques which inspect by using single wall single image technique, panoramic technique, double wall single image technique, double wall double image technique. The equipment and tools are gamma ray source system, radiographic films, cassettes, and intensifying screens, lead markers, IQI, penetrometers, weld specimen, magnetic stand, safety gear, exposure calculator. First of all, we'll show the inspection which is using single wall single image technique. This technique is applicable for both plates and pipes. Primarily intended for pipe diameter of 100 mm and above, where access is permitted. The procedure is: after finished from film loading, start to perform this technique as visual inspection of the specimen, examine the welded specimen visually and note down any surface defects. Choose the appropriate IQI type according to the sample thickness of the same material as that of the specimen. IQI should be placed in a proper manner on specimen I.E source side and wires across the weld. Place the film underneath the plate. Place the lead letters. Set the source at right angle with the film and weld seam using magnetic stand. Set the specimen at a proper distance. It should be more than minimum distance that you can calculate it by the rule. Calculate the exposure time by application. Process the films inside the darkroom. The second technique is panoramic. It should be performed for pipe of outside diameter from 12 inch. The procedure is: after finished from film loading, start to perform this technique as visual inspection of the specimen, examine the welded specimen visually and note down any surface defects. Choose the appropriate IQI type according to the sample thickness of the same material as that of the specimen. IQI should be placed in a proper manner on specimen I.E source side and wires across the weld. Place the lead letters. Wrap the films around the welded pipe. Set the source at the center of the pipe using the magnetic stand. Calculate the exposure time by application. Process the films inside the darkroom. The third technique is double wall single image. It should be used to radiographic pipes of 3.5 inch diameter and above when internal access is not permitted. The procedure is: after finished from film loading, start to perform this technique as visual inspection of the specimen, examine the welded specimen visually and note down any surface defects. Choose the appropriate IQI type according to the sample thickness of the same material as that of the specimen. IQI should be placed in a proper manner on specimen I.E source side and wires across the weld. Place letter F, which is mean film side. Because of the other technique is source side, wrap the films around the welded pipe. Place the source at an angle of 10 degrees far of the cap of the weld as you see. To take the film from inside. Calculate the exposure time by application. Process the films inside the darkroom. The fourth technique is double wall double image. It should be used for pipe has equal or less than 3.5 inch of diameter. A technique can be used in which the radiation passes through two walls. The procedure is: after finished from film loading, start to perform this technique as visual inspection of the specimen, examine the welded specimen visually and note down any surface defects. Choose the appropriate IQI type according to the sample thickness of the same material as that of the specimen. IQI should be placed in a proper manner on specimen I.E source side and wires across the weld. Place the lead letters. Calculate the required geometrical unsharpness factors for both superimposed and elliptical techniques. Wrap the films around the welded pipe. Set the source at right angle with the film and weld seam using the magnetic stand and be careful to place the specimen at a proper distance. Calculate the exposure time by...
Tingnan pa natin yung iba, ha? Kasi namimili lang tayo ng kung anong kung anong magandang eto.
Help nourish them with the goodness of milk and wheat from Tiger.
Radiography testing utilizes ionizing radiation
Nadidinig ba, Hana? Okay ba?
to achieve an
Yes po.
Sige.
image of an object on several different viewing medias. This may be gamma rays, or as in this case, X-rays. The examiner marks the weld to be inspected with a measuring tape. This will be visible on the X-ray. Thus, he will know how to determine the exact location of possible irregularities. The film is mounted on the object, and the X-ray tube is set up carefully. The examiner leaves the area, closes the lead door, and operates the device remotely. This way, he avoids coming into contact with the radiation. He adjusts the voltage, current, and duration, depending on the investigated material and the wall thickness. Then he starts the irradiation. The X-rays go through the material and generate a radiographic image on the film or imaging plate once processed. The experienced eye of the examiner interprets the image, and he can now determine the quality of the inspected object and if it meets the standards. X-rays can also be used to establish the authenticity of paintings, for example. Through the centuries, paint contained different quantities of lead. By exposing the paint layers to X-rays, it is possible to establish whether a cloth was repainted and the period from which the paint layers originated. In this case, the radiographic image is recorded on an imaging plate. Use image is read. Art experts can use this to determine the authenticity of the painting.
So okay na ba 'yon? Yung ano ba 'yon? Magnetic. Ito radiography, no? So tingnan natin yung magnetic.
Hi, my name is Mike Porter. I'm a corporate NDT Level 3 for Alta Vista Solutions, and this is part of a video training session, and we're going to be
Nadidinig ba, Hana?
performing
Nadidinig?
magnetic particle testing on a painted component.
Okay naman, sige.
So what we're going to do is we're going to demonstrate the proper technique to perform magnetic particle testing through a layer of paint on a component. Typical applications from ASTM E709 is the particular standard that we're working to, the American Standard Testing of Materials, and it doesn't allow you to test through paint. You need to test through uncoated surfaces. You're allowed 1 or 2 mils of paint, and then that would be acceptable. But if it's a special application like this particular component has about 16 mils of paint on it. So in order to test through this, you need to be able to demonstrate that you can find the particular anomalies that you're looking for and demonstrate the technique. So this is a magnetic particle yoke. We're going to start over here. One of the things that we teach our technicians is the proper technique to applying the particles. As you apply the particles, you want to actually just float them on. You don't want to dump them on with a can such as that. You just want to be able to lightly float the particles on. And the same thing with a puffer. When you blow the particles away, You want to be a little tender and a little sensitive and make sure that you have the right technique. We're going to move down across the plate, making sure that we have overlap. So I make sure that I test 100% of this particular component. I don't see anything there. I'm going to move down again. And as I apply this here, we actually start to see the formation of an indication along the toe of the well. That happens to be about a 2-inch long crack in the heat affected zone. So as I talked about before, that it's important to know the techniques and the proper technique of blowing the particles off, because if I use too much force, especially on a painted plate as opposed to an unpainted plate, I can actually blow the particles away and you no longer see the crack. So again, it's important to have the proper technique in floating the particles on and watching them form, and then also the proper particle removal with the blower. So this completes this particular video training session on performing magnetic particle testing on a component that has a layer of paint. Thanks, and have a great day.
Kuha pa tayo ng isa ha. Yung actual. Na ano ba? Nadidinig ba, Hana? Nadidinig? Umpisahan natin uli ah. So last na lang, no? Yung last na lang natin ay yung sa dye penetrant, no? Dye penetrant.
Demonstrate something for. Welcome to Weld.com. I have Garrett Vickery with us today for, he's our NDT instructor, our new NDT instructor. And I have asked him to come down and demonstrate something for us. I think we've talked about processes for non-destructive testing, one of them being dye penetrant. And there are a couple of methods of dye penetrant. Garrett, we've got just regular old the spray can dye.
Yep, just typical red dye, visible penetrant. No fluorescence, no black lights necessary.
Okay, but since you mentioned fluorescent, that's the other one that I was kind of wanting to lead into, and
Correct.
that's the one that you put the, what is it, Zyglow looking stuff in there and light it up in a black light.
Yep, bright green as opposed to the red.
Being old and blind like me, if I can't see it, you're going to say, well, come over here and I'll really show it to you.
Right.
That's kind of that deal. I think I made, and I want to do this, I made a test sample for your program a long time ago, and it was a groove weld, and I put a piece of copper in the weld metal and I welded over the top of it, and it just makes it crack. Okay, and I came out of it, it was a big old thick piece, and I think when I got to the very last pass, you really couldn't see it visually.
Covered it up, yeah.
But man, when you lit it up with the old black light, it was like a spider web just screaming at you. So you brought down a couple of samples here, one of them being a test sample, a Flawtech test sample, and I see a little bug hole, a couple of things in there. You know, just looking at that from the outside, we don't see, I mean, the weld's been kind of sanded and cleaned up a little bit. Looks like we've got some surface rough from people handling it. And there's some toe indications on there. Not that bad of a root, but it looks like there might be something going on with that root as well. And then the other one you brought down is a piece of titanium, 6.4 titanium.
Grammarly helps you work more efficiently, which makes accomplishing your work goals easier than ever before. Get full sentence rewrite suggestions.
And just, you know, I mean, to me, looking at the bead doesn't look that bad as far as profile, a little flat, but what I'm seeing are some indications that kind of arc off across here. Now, I don't know what you're going to pick up with the B-roll zooming in, but to me, it you know, it looks like it's got some kind of a crystalline look to it, or something like it tried to crack. Maybe lack of trailing shield or something. Maybe it cooled off too quick. I don't know. So, what's the process here? What are we going to do?
So what we're going to do is, like you mentioned earlier, is I've cleaned the surface there, because with the surface inspection, if your surface isn't pristine, then it's a worthless inspection.
And then, this process just lends itself to surface. We're not surface and very minor subsurface stuff. So porosity, lack of fusion in the toe, and maybe some of if there's a crack in here that's coming off of that weld.
Correct.
Okay.
All of it has to be open to the surface.
Okay. So we're going to shoot some blood on there first, and then
here, apply it, and we can apply it by spraying it, dipping it. We're going to brush it today in the essence of control. And then we'll allow that to dwell, and utilizing the penetrance property of capillary action, it's going to creep.
Good word. I think I used that in here before for brazing techniques.
Yeah.
Nice. Welcome to our world.
Creeps in there, gets into things that are open, and we let it set.
Okay.
Then we're going to wipe it off as clean as can be. We don't want to see any more red after we wipe it. allow that to dry for some time because we're going to use some solvent to assist in that, and then go back over with a developer that's going to reverse that capillary and pull out anything that was left inside of there.
So the developer would be like a contrast.
Correct.
Like what,
yeah,
a
bright white as opposed to the bright red there. Right here is what we're using.
Okay, so once you put the developer on there, I mean, just turn it kind of a white talcum looking stuff on there. But if I see any bleeders, any red spots, you just know right in a hurry. Okay.
Oh yeah.
Interesting.
And we'll see the evaporation of that happen. You'll see it kind of come in on itself, and then it's interesting to see.
Okay. Well, let's do the
light
penetrant.
Light brush here. I'm just gonna apply it.
Wow, that went quick. That stuff's pretty thin and thin flowing, isn't it?
Yes, sir.
It'll get right down in any known surface flaws.
A little will do ya, but over time, throughout that dwell time, it'll start to kind of coagulate, similar to blood, and we want it to stay nice and wet, so we can re-wet it throughout that dwell time, which will take us 10 minutes.
Dwell time, it's like your 10-minute set time. That's
correct.
Okay, so we're going to let this set for a minute then.
Yes, sir.
We'll be back in a few. Welcome back. We have let this set for a good 10 minutes. Like you said, it kind of coagulated. It got a little thick, didn't it?
Yes, sir. But we re-wetted it periodically.
I'd touch that, but I'd wear it for a couple of days,
yes,
wouldn't
sir.
I?
Oh, yes.
Okay.
Just in handling it, I've ended up looking like a red leopard, but we went.
So now the process is to wipe excess off?
Correct.
Okay. So
we're going to go ahead and start wiping here. Just first off, start with a paper towel and get it off of there. And then we'll go back through with a solvent dampened cloth to get it the rest of the way.
And take anything else off.
Correct. It gives you a good background to pop off of too, so it just sticks out at you. There's no fail.
It's either good or bad. That's what you're saying.
Yes, sir.
I'm really hoping that opened up. That titanium weld, I mean, it's a decent looking weld for profile, but again, there's just something funny about it, the way it looks.
Nakita ko na yan dati.
Oh, welcome back. We've let our solvent evaporate. Mr. Vickery is getting ready to throw down with some developer love here. So this is the white contrast.
Correct.
This is what's in that stuff.
It's a cakey consistency, almost like powdered sugar.
Okay, so when you spray that on there, it's going to be, we got to wait, or by code we got to wait, but you'll be able to see something fairly quick.
Correct. Like I said previously, it's an involved dwell time, as opposed to earlier, you can just walk away and come back and re-wet it periodically. We want to watch the evaporation happen, and that'll make sense here in a moment.
Okay. All right.
Great. When I'm doing this, I want to start off of it and finish off of it, because if I spray direct, we could blow something out.
Okay.
That's kind of how we're going to do that. And too little is far better than too much, because we don't want to cover up.
So you could essentially cake that on there to the point where you just...
Correct. See what I'm referencing here? It's coming in a little darker, and then it kind of closes together on itself.
Wow. So they've got a lot of indications all down the toe of that weld. And that's a major bleeder right there.
That's correct. And looks like I missed there on that one.
That does look a little light on this one here.
Far better to have less.
I'm noticing something way down here on the end, but then I'm noticing along the toe of the weld, I'm seeing a little bit of indication. I'm not seeing these arc things that just look like cracks that come off of this grain in this weld. I'm not seeing those open up at all.
It very well may be they're not open to the surface. They could just be there, you know.
Why is the toe, I mean, it's showing a little bit, not like this down here.
That's a little bit of that non-relevant red that we were talking about previously, as opposed to this deep.
This is down here?
Correct.
Non-relevant, meaning you just didn't wipe it all off.
Correct.
So in that case, you'd go in there and would you clean the entire thing off or just that part of it?
Yep, I can just spot wipe that, redevelop it, and if there's enough penetrant like this one, I could wipe it 2-3 times and it'd still keep coming back because it's trapped enough penetrant there. Whereas that one, it wouldn't come back even after the first try.
So now by code we're gonna wait 10 minutes?
Correct.
But we don't need to on the one closest to you. That's a bleeder. That has problems. So as an NDT person, are you calling out what it is other than the fact that, you know, it's a bleeder? Are you going to make the determination that it is lack of fusion?
Yes, sir. Because depending on the type of indication, where it's lack of fusion versus a little surface porosity, like we even have a couple of little 1, 2, 3, 4 dots there of some surface porosity.
Out here in the
they have different tolerances for undercut versus lack of fusion, one being more critical than the other. Okay. So we have to have that knowledge where it's a good partnership between welding and NDT to know how that process works, to give you that foresight.
Okay, so obviously we don't need to wait the 10 minutes. This one here, I don't want to move it because it's set for the camera. Are we seeing anything in this one here that would cause you to call that one out?
This sharp fine line right here could possibly be geometry, the way that they blended that together, but to me, I believe, you know, better
on the top side toe of this
Correct.
weld here is what you're saying.
Correct.
Okay.
Possible lack of fusion.
So, but I wouldn't think so. Looking at the weld on both sides and studying the weld, I don't know that that's lack of fusion. I'd go back to geometry. So what if we rewipe that real quick?
Yeah.
And shot it again. So I'm just going to wipe heavy along the toe of the weld.
Let's see what happens the second round.
By far less, but I'm still seeing something right here open up.
Yes, sir.
Color differentiation. Huh. Okay, so
Patong-patong na discounts. Add to cart na! Mag-Milo everyday para tuloy-tuloy ang energy magpursige.
the one closest to you is obvious. It's got problems. That's rejected. Okay. This part here, it's still in suspect.
Correct.
What would we do at this point?
We would demand a little more sensitivity, with visible being on the lower range of that.
Okay.
On a system quality panel, it'll get a half of a star. So there's 5 starburst cracks on a sensitivity panel, and it'll get 1, but the industry technically calls it a sensitivity level 0, where we'd have to step into the fluorescent booth and demand that higher quality.
Fluorescent?
Correct.
So that would be a good candidate to go light up with the black light. And
yes, sir.
Cool. Let's go do that. You want to?
Yeah, sure.
All right. Okay, so we had the fluorescent penetrant on there, and now you're rinsing that off, just
Correct.
like we did with the developer thing. You, anything in control here as far as
yes,
code-wise? I mean, pressure, temperature,
all of those things, yes, sir, and distance away from the part as well.
Really?
Yes, we don't want to be right butted up on here and spray, and then because we'll blow out where that penetrant is staying put.
So we're cleaning the part, got certain temperature and pressure of water, and you're just kind of, you're 10, 12 inches away, you're not blasting right down on top of it.
Correct.
Okay, so you doing any wiping from here, or just letting it air dry?
Wiping. Yes, sir, and we have a dryer here that is at a, also temperature-wise.
Yeah, I can feel that's nice and warm.
Yes, sir. And I don't want to lay it flat on this rack here because there could be residual penetrant there, and that would show up. Definitely. So we'll just let that dry.
Okay, nice warm air. How long would we go for that?
That's also 5 minutes.
Everything is 5 and 10 minutes.
Everything takes time. It's hurry up and wait, Bob.
Okay. All right. So we go 5 minutes of dry time on here.
Correct.
All right.
And we'll be back for the developer.
All right. We'll be back in just a second. Welcome back. We shot the dye penetrant on here, and we're getting ready to. We rinse this thing off. We let it dry for the appropriate 5 minutes, and we're getting ready to do an indication here, or the final part of this underneath the black light. Okay, so we're clean and dry. Visually, I don't see anything on here. Let's put it underneath the black light and see if anything lights up. Can you drop that down a little bit, please? Oh, I can see all your fingerprints.
Process controls.
Okay, so actually you're up here to do the test up in the viewing window. Bring it up here just a little bit. I see absolutely nothing in that whole piece.
And that's a testament of, visually you can swear something.
I would have bet the cameraman's something in the way that green structure laid out and went transverse across the weld and even got over into the parent metal. I swore there it would have shown something in there, but it shows absolutely nothing. Okay, I'm seeing, aside from your fingerprints, I'm seeing little bitty dots. What is that? Anything on the surface of the metal, or is that something that's just on there?
That's just a process control. It's similar to the non-relevant with the visible penetrant.
There's nothing. I mean, you can at this point wipe it off and just see if there's something on there.
We have that same process.
So I just lightly touch that with my finger. It disappears.
Go back over it. With fluorescent, we use a dry powder as opposed to the aerosol can because it's a little less invasive.
Okay. And again, wow, that's crazy.
It may not be pretty, but still structurally integrity.
Wow. Looking at this thing, when we had this thing out on the table, when we did the regular, can I wipe this off with my finger? This grain structure just looks strange to me. And you get this in the light, the right light, and you see these things arcing off across here. Man, I would have thought that those would have opened up in the crack. Nothing.
That's cool. True test. We could bin test it.
Well,
See what happens to that. See if she holds up.
You guys are non-destructive. I'm destructive.
Yeah.
Well, a bin test would be a soundness test. Nothing to do with that. What would be the next test?
On my end of the world, we could try like a magnetic particle. Since this is only surface inspection, mag particle, we get a little penetration underneath the surface to see if those things pop up that direction.
Okay, well they're not popping up to the surface, so how would they? I mean, that's interesting. So if we did a destructive test or using some other method, X-ray or whatever, we would be looking interesting stuff. I appreciate your time. That was I learned a lot, and I hope you did too. So, thanks for watching weld.com. Please subscribe to our videos. Thank you.
So, okay na. Balik tayo dito sa natin, lecture. Nakikita na ba yung screen, Hana? Nakikita na? Hello?
Yes po.
So balik tayo dito, no? So, etong fracture toughness and fatigue, no? Hindi mo makikita yung kanyang characteristic or hindi mo siya ma-interpret kung hindi ka gagamit ng mga methods. And foremost of which is yung NDT. Di ba? Kasi yung fatigue is bunga ng cyclic load, and then makikita mo una kung saan or kailan or paano siya nag-start. So normally mabagal siya, di ba? Tapos papabilis. So hindi mo siya makikita kung naked eye lang, no? So gagamit ka ng mga non-destructive testing, ibig sabihin yung hindi ka gumagamit ng mga paninira or nag-a-apply ka ng load na nakakasira, no? Ano 'yon? UT, summarize lang natin, yung UT is ultrasonic or ultrasound, using ultrasound, di ba? Nako-convert yung mga signal ng tinatawag na discontinuity or mga flaw or mga defects, no? For example, kung may butas, kung may tabingi, kung mayroong crack sa loob, no, nakakalibrate yung height, no? Yung surface niya nakakalibrate. And then when you do that, you have to use yung tinatawag na gel and yung probe, no? So, kung mayroong mga crack, kung mayroong mga discontinuity, mayroong uka-uka na nade-detect yun, no, sa using the machine, no? Another is radiography, no, yung X-ray, 'di ba? So parang pag nag-X-ray ka ng dibdib, ng lungs or ng ngipin, no? So makikita yung kaloob-looban. Magnetic particle, no, yung it has to respond doon sa material, no, na para maging electromagnetic ano siya, no? And then nagbibigay din ng signal doon sa machine or sa equipment. Then yung huli, dye penetrant, dye has to do with colors. No? Nakita nyo may parang pinipintura o pinapahid na kulay. And then ang nakakapag-interpret lang yan ay yung metallurgist. No? Kasi yung mga grains, yung mga structure, yung mga linya-linya, yung mga surface, alam nila yan. No? So when they use the dye and then dine-develop nila, no? Kasi may developer, dine-develop nila into parang ano siya, no, parang developing ng color, no, makikita nila kung ano yung nangyayari sa process, no. So ito yung mga NDT na ano natin na mga test, no. Okay, meron pa dito, no, ultrasonic at hindi pa natin nakuha tong ano to, eddy current, no, tungkol din naman sa current, no, and then ko-convert yung signal kung saan merong mga deformities or may mga defects. Ano pa? Acoustic emission has to do with sound trend, and then yung leak test, no? Yung leak test, no? So later na natin to anahin, no? Titingnan, no? At least na nagkaroon tayo ng idea tungkol dun sa mga NDT, 'di ba? Sa ultrasonic, sa radiography, tapos yung sa ultrasound, 'di ba? Tsaka dye penetrant. Okay? So I think yun muna ang ano natin, no? Itutuloy natin yung lectures sa next week. And after next week kasi ano na natin, midterm, no? So kailangan nating ma-take up eto, no? I-flash ko lang. Ano ko lang ha, sandali. Para makapag-dismiss na tayo, no? Kasi 3 mayors. Nakikita ba, class? Nakikita ba, Hana? Yung naka-flash?
Yes po.
So ito tayo, no? So looking back at the curriculum, itong syllabus, no? Ito yun, no? Na take up na natin yung types of engineering materials composition, chemical bonding, no, yung mga amorphous crystalline partly, no. So tingnan natin kung ano pa yung matututuhan natin dito, but we're going to finish dapat yung properties and characteristics of materials, corrosion prevention and control, no. So dito lang tayo, properties and characteristics of materials, corrosion prevention and control. So next week we're gonna discuss yung corrosion and how to prevent and how to control, no. So yun na lang ang aanahin natin. So we are on time kahit may nagpapabreak naman ako sa quiz and so on. And yung mga quiz nyo, congratulations, magaganda naman yung result, no. So I think yun muna, maraming salamat, and I'm gonna start yung presenting and then yung recording, no, recording kasi ni-record natin to para kung may maghihingi sa inyo ng didiretso to sa email ko, no, pero pwede kong i-share sa inyo, no. So at least meron tayong reference dun sa mga na-take up natin. Stop recording ko na, no?